this is kind of a norm, right? So when we take a complex, function and evaluate this, this is a norm, or it's a density. It's not really a norm. It's not a density. So, so one of the postulates, and it's really the Born interpretation in disguise. One of the postulates of quantum mechanics is that for realistic systems, psi must be an L2 integrable function. Okay. So what does L2 integrability mean? It means that if I take the modulus of psi squared, okay, let me just write their argument, the modulus of psi squared, and integrated it over all space, then this will not diverge. That this is some constant, say n, and this will not diverge, okay? So this is what it means for a function to be L2 integrable. Okay. Is that clear what it means?
Yes, sir.
Yeah, makes sense.
So this 2 refers to this exponent. Okay, why it's not L cubed integrable, why it's not L4 integrable, we don't know. Okay. So if this is true, then we can always replace our wave function psi by 1 over square root of n of psi. And this new wave function will be normalizable, right? So this guy, let's call it, say, psi prime. So psi prime of xt is 1 over square root of n psi of xt. Then the integral of psi prime of xt over all space will be 1, right? Another thing is that, see that in the normalization, it doesn't matter if there is a phase here. If, say, here we introduce a phase, a constant phase, E5, right? It drops out of the normalization. And in fact, in quantum mechanics, we identify all wave functions which differ from each other by a factor of a constant phase. Okay? So this is a constant phase. And this means this is an identification. It's an equivalence relationship. So it's actually a projective vector space. Okay. Anyway, we'll return to that later on. So although we impose the L2 norm condition, Now, there are an important class of wave functions which represent idealized plane waves which are not L2 integrable. We are forced to introduce them. They are kind of an over-complete basis, but it makes life very easy to actually include them. And these are essentially the plane waves that we saw. So there's some constant times e to the power minus I kx minus omega t, right? So it should be obvious that if I take psi star psi, that is a constant, and therefore, this is not L2 integrable, right? Because if I, integrate something over, sorry, that's my cat. If I integrate something over a constant over all space, we are going to get an infinite number. However, it still has an interpretation
Sir, I didn't understand from the E phi part, e to the power I phi part.
Oh, basically we're saying that, so if I start here, suppose that the norm of my wave function is some real number n, then if I replace my wave function by the original wave function divided by square root of n, then this new wave function, which I can call psi prime, that wave function is normalized. But if I now multiply this wave function by a constant phase, then this does not change this normalization condition, does it?
Yeah, this part I didn't understand. How does it not change it?
Because here we are taking the modulus, and what is the modulus of a phase?
It cancels during
Yeah.
the multiplication.
Yeah, so it doesn't affect this. And it's one of the assumptions of quantum mechanics that two wave functions which are related by a multiplication of a constant phase describes the same physical system. Okay, so this is irrelevant.
So what's the advantage of this e to the power I phi?
There's no advantage. This is just like physically this thing and this thing is the same thing.
Oh, okay, got it.
Is this
So-
related to the idea that phase velocity is not doesn't describe anything?
No, this has nothing to do with phase velocity.
Oh, I see.
Yeah. This is just projection. It's just it means that the vector space that we are dealing with is a projective vector space, where two vectors which are proportional to each other up to a non-zero proportionality constant are the same, meaning that only identity vectors, only vectors, unit vectors have any physical interpretation. Okay?
Yes, sir.
Okay. So so then we are saying that although we impose the L squared norm condition, there are an important class of wave functions which represent, say, the idealized plane waves, which are not L squared integrable. So they are this type, And if you look at the psi star psi, it's some constant. And therefore, it's not L squared integrable. However, these guys still have interpretation in terms of relative probability. How so? So suppose that I want to discuss, suppose you have some system which is described by this wave function. And I want to ask, what is the probability of finding the particle in this interval versus the probability of finding the particle in this interval? What do you think? So this is the probability density. So it's c squared times.
Should it be same on both sides?
Let's see. So the length of this thing is 6L, where this is, say, L. So the probability density is, say, c squared. So the probability, the relative probability of finding it here is c times 6L. Whereas the relative probability of finding it here is going to be c squared 2L, because this is 2L. And therefore, the probability of finding it here is going to be 3 times the probability of finding it here, right?
So we're just comparing. There's no absolute value attached to that
Yeah, exactly.
probability.
Yeah. You cannot normalize it. You can just compare, right? So this is to justify why, also we will need this because even for L square integrable functions, we can express them in terms of linear combination of such functions. This is known as Fourier analysis, which we will study in a little bit, okay? So these are very useful. These are basis. These are going to act as basis vectors for that. For that description. Okay, any questions?